Hi everyone, welcome to the lecture series on structural dynamics. In this lecture, we will be discussing on the resonance response to the single degree freedom system of harmonic vibrations or force vibration. In this class, we will discuss both when the system is undamped and the system is undamped. Let us first start with the undamped system. How does the response when in the resonance condition? So this is the, let us say, undamped case. We'll correct this. So this, let us say this is not there, or this is equal to 0. So then this is the response as we discussed in the previous lecture series, that x of t is xs t by 1 minus beta square sin omega by t minus beta sin omega t is a response for the undamped systems for a harmonic vibration. Now what happens when beta equal to 1? That is a resonance condition. The sin omega bar t can be converted as sin beta omega t. Now that means at beta equal to 1 it becomes 0 by 0 form, which is not defined. Then we can use L'Hospital rule to solve the problem. That means differentiating the numerator and the denominator separately with respect to beta till we don't get 0 by 0 form by substituting beta equal to that value, that is beta equal to 1. So if you go on differentiating 2 times, one more time, so what happens? We'll get one time differentiation is xst omega t cos beta omega t minus sin omega t by minus 2 beta. When beta equal to 1, now we don't get 0 by 0. So that means this will be the response when beta equal to 1. Substituting beta equal to 1 here, so what we get? X of t will become xst into sin omega t minus omega t cos omega t by 2. That is the response at the resonance. We call it as d of t, the response at resonance. So now if we try to plot this sin omega t minus omega t cos omega t by 2, taking some values of xst, or we take a ratio x of t by xst or d of t by xst with respect to sin omega t minus this thing, what happens? So this is what danger happens when system is in resonance. So over a time, very short time, see the amplitude of vibration goes on increasing gradually without changing any force. I am not increasing any force here. Neither stiffness change, nothing is changed. Just over a time, amplitude goes on increasing. This is the danger of the resonance condition. This is for the undamped system. So now let us look at a damped system. So the response with the dynamic amplification factor, what we learn is 1 by 1 minus beta square whole square plus 2 xi beta whole square. Then at beta equal to 1, what happens? This is 0. So 1 by 2 xi. Right? So maximum displacement becomes 1 by 2 xi. So value depends upon the what is the damping ratio we choose. But if you look at carefully, what is the maximum dynamic amplification factor? That means we'll differentiate this function with respect to beta and equating to 0, we get a maximum dynamic amplification factor, or d. So that we get at beta equal to, by differentiating, let's say d of d by d beta equating to 0 like this. So then we get a beta value. This is equal to 1 minus 2 xi square. By doing that, we'll get it. That means basically what I'm doing here, d by d beta equating to 0. So I get beta is under root of 1 minus z square. That is a root. By substituting beta into this d, then I get a d max. So that d max becomes 1 by 2z under root of 1 minus z square. Of course, after so many simplifications, we have to neglect certain terms. Okay. So again, if you look at the d max at beta equal to 1 and d max by equation 2, they are very close, because we know xi square is small, xi square is very small. That means 1 minus that is very close to 1, under root 1 is 1. But if there is a damping, is substantial damping is present, then these two are different. But otherwise, the difference can be neglected. That means the maximum amplitude need not come always at beta equal to 1. Slightly beta of this also happens. So that beta equal to under root of 1 minus 2z square. Although resonance takes place to 1, but maximum peak amplitude occurs at beta equal to under root of 1 minus 2z square. So if we look at the nature of resonance response, the x of t becomes xst by under root of 1 minus beta square whole square plus 2z beta whole square sine of omega bar t minus psi, plus this is the transient response. Right, now taking the beta equal to 1, then this psi will be 90 degrees, because 2z beta by 1 minus beta square. So tan inverse of infinity is at 90. This response will be this, substituting beta equal to 1 and xi equal to 90. So this is what I get response. Then using the initial conditions, that means at time t equal 0, initial displacement is 0, initial velocity is 0, and solving for this response, and by neglecting some terms like z square and sin omega dt multiplied by xi term, xi multiplied by sin omega dt terms, neglecting that. So we get a term something x of t is xst by 2z under 1 e to the power minus xi omega t minus 1 cos omega bar t. So this is the response at a resonance. This is to simplify. Otherwise, we can neglect very well this. I'll go ahead with this, which is steady state response. Mostly we do that. So this part is very negligible. But if you don't want to neglect, also we can have this. So that means the resonance response in terms of time is 1 by this xst can be brought this side. So x of t by xst we call d of t, the ratio of amplitude of dynamic to the static. 1 by 2z e power minus j omega minus 1 into cos omega bar t. So if you plot this response with the time, what we observe is this. See, now the amplitudes are increasing exponentially. After some time it is static, constant. So this is because there is a damping. So that fear of is not there when you go after some time. Constant amplitude maintaining after some time, but for initially high amplitude. So this is a response for the at resonance when there is a damped system. Thank you.